All right, here's my video for lesson 532, where we're going to learn about the law of sines. And so just to remember where we're at right now, we did lesson 531, and what that lesson showed us was that there's a lot of triangles that we don't know how to solve for. In fact, anything that's not a right triangle, we don't really have tools for. We think about all the tools that we have at this point when we hit lesson 532, and we have the Pythagorean theorem, we have sine, cosine, tangent, we have inverse sine, inverse cosine, inverse tangent, we have our 30, 60, 90 rules, our 45, 45, 90 rule, and our Pythagorean triples, okay? All of those, all the ones that I just listed, those all work on right triangles. But we have no tools that work on non-right triangles. And so that's what we're going to try to learn here with the law of sines. Okay? Now, what we're going to do as we work through this lesson is we're going to see the old way of how we could use to solve for it, like we would have done in lesson 531, and then we're going to develop our new way, which is going to be this law of sines. Looking at number 2, the idea here is to start developing this this idea that there is a relationship between the angles and the sides across from the angles. All right? And what that relationship is that, and the way I say it, is that the bigger the angle, the bigger the side across from it. Okay? And I like to think of it, okay, this big angle is creating this big side. Okay? Now, the smaller the angle, the smaller the side it creates. So using my triangle sum theorem, 63, 105, that means this angle here must be 112, so now they all add up to a 180. Now that's the smallest angle, so it must be creating the smallest side. So just looking at the angles of a triangle, I can tell you which side is the biggest and which side is the smallest. All right. Now this is just a relationship between angles and the side lengths across from them, but that's going to come to play when we start talking about the law of sines. Okay. Looking at this problem here with Madeline, do I agree with her or do I not agree with her? Well, what she's saying is I don't think this diagram is drawn to scale because I think the side labeled X should be longer than the side labeled 4. Well, with this newfound idea that the angles create side lengths across from them, well, 42 creates this side length, 26 creates this side length, big angles create big sides, and so 42 should be, or this X side should be bigger because the angle 42 is creating it. And so I actually agree with Madeline here, and I think that this side X should be longer because 42 is bigger than 26. Okay? Again, there is a relationship there between angles and the sides across from them, and we'll see that get solidified with the law of sines. Now, Layla is going to look for how to solve for X in this triangle. And we did something like this in lesson 531, and what you do is, well, at this point, we don't know how to do anything other than right triangles, so let's create a couple of right triangles here. I draw a line straight down, and now I have a right triangle on the right, and I have a right triangle on the left. First step of trying to solve one like this would be to find H, this height of the blue line H, and we can do that by using our trigonometry. Okay? If 42 is my angle, H is opposite, 4 is the hypotenuse. Opposite hypotenuse tells me to use sine. So I do the sine of my angle, which is 42, equals the opposite over the hypotenuse, which is H over 4. Now I put this over 1. I can cross multiply and solve here, and I believe I get H equals about 2.68, approximately. So now that I know H is 2.68, I can then use my left triangle here, the triangle on the left, to solve for X. Again, I'm going to use trigonometry here. I have my angle 26, the 2.68 is my opposite, and X is my hypotenuse. Well, opposite hypotenuse tells me this is a sine problem. Since I'm using the triangle on the left and the angle 26, that is the sine of the angle 26, equaling opposite over hypotenuse, the opposite being 2.68, and the hypotenuse being X. I put that over 1, and again, I cross multiply and solve, and I believe I get an answer of 6.11, rounded, so approximately that. Now, the area of this triangle, I'm not going to work this completely for the time of the video, for the sake of the video, okay? But what we would need to do is we need to find this base of the triangle here, okay? Because we have the height of the triangle. We found that to be 2.68. We need to find the base. Now, how you would find the base would be to say, okay, I have my triangle on the right, use trigonometry to solve for this distance y, which is just the adjacent side of this right triangle on the right-hand side. Then what you could also do is look at the triangle on the left-hand side and solve it for the adjacent side w. Now, if you add the adjacent side w plus the adjacent side y, you would get the entire base b. Then all you would need to do is use 1/2 base times height. You have your height being 2.68. You have your base being your b, or your w plus y, and you just plug it into the equation and solve. Okay? So if you get an answer, you can write it down there. I'm going to skip that one for time reasons. Here, we have our kind of introduction, getting closer and closer to developing the law of sines. What they're saying here is we're using, Ty is using the sine of 58 equals h over 12, so that's sine of opposite over hypotenuse of this triangle on the left. And Ivan is using sine of 24 equals h over 25, and so Ivan's using the triangle on the right. And there's your answer for A. He's using the triangle on the right. Now again, I'm not going to calculate this one out because you could do it using trigonometry, but you can calculate both of these out and solve them for h and see what do they equal. And without much of a pause here, I should tell you that h is going to equal the same no matter whose you use. If you use Ivan's or if you use Ty's, the h's are going to be the same. You're solving for the same h right there. Okay? Now that kind of plays a bigger role. The reason I talk about that is it plays a bigger role when we get into the law of sines, which we'll do right here. So looking here, we're going to develop the law of sines, but first what we're going to do to start developing that is write two expressions for h using this triangle to the right. So what I'm going to do is I'm going to call this angle here angle B, and I'm going to use a capital B. And I'm going to call this angle here A, and I'm going to use a capital A. And now I'm going to set up equations and have it h equals something by the end of it. So using angle B, what I'm going to do is the sine of angle B equals the opposite over the hypotenuse, which is h over A. I'm trying to get this to be h equals something, and so what I'm going to do here, a little trick, is multiply both sides by A, and here's why. On this right-hand side now, A here from the multiplication is going to cancel with A here from the division. So what I'm going to be left with is h equals A times the sine of the angle capital B. And that's one of the expressions they wanted me to find, one of the two expressions. The other one comes from the left-handed triangle. So that was the right triangle, the right-handed right triangle, and now this left-handed right triangle. We're going to do the same kind of thing. We're going to do the sine of angle capital A equals opposite over hypotenuse, which is h over b, and I'm going to multiply both sides by b, so I can get some canceling out here and get h by itself. So b there. All right, after we get our canceling out from this b and this b, we will be left with h equals b times the sine of angle capital A. And that's my second expression of the two they wanted. H equals this and h equals that. Now, like I just said in slide 4, those heights, those h values are the same. Just two different triangles solving for it, two different equations to solve for the same h. Well, since this equation equals h and this equation equals h and those h's are the same, we're allowed to set those two equations equal to each other, which I'm going to do down below. So I'm going to set this here equal to this here. And what I get when I do that is I get a times the sine of angle capital B equals b times the sine of capital A. Now, ultimately, what I'm going to try to do is get it to look like this up here, look like this equation here, because this equation here is my law of sines. So what I've been doing, kind of secretly hidden in here, is I'm deriving the law of sines from a generic non-right triangle. Anyway, picking up where we left off, I'm trying to get it to look like the law of sines. So what I'm going to do, a little move here, is that I'm going to divide both sides here. So dividing both sides is not going to change what I'm doing. It's perfectly balanced. All right, I'm dividing this side by a times b, and I'm going to divide this side over here also by a times b, and you'll see why. But I'm allowed to do that because I'm doing it to both sides. Now, when I look at this, I have a on the bottom, a on top. I can cancel those out. And so I'm left with the sine of angle capital B divided by the little b, because a is canceled out. I can set that equal to, well, on this side, the b's are going to cancel out. I got a b on bottom, a b on top. They're going to cancel. And I get the sine of angle capital A divided by little a. And there's the formula. I have derived the entire formula there. Okay? Now, what this means, the deriving of that formula is not crucial, but it does show you where it comes from. But really what it means, in looking at the diagram, what it means is that I have the sine of my angle divided by the side across from it, equal to the sine of my other angle divided by the side across from it. Okay? And that's what they're trying to say in part C, is angle B is located in relation to which side labeled B? Well, they're across from one another. Let's see how we apply this law of sines in this last problem here. Okay? In the last problem here, they give us the law of sines, and they're telling us to use it on this problem here. Well, the law of sines is choosing an angle, doing the sine of an angle divided by the side across from it equal to the sine of the other angle divided by the side across from it. Let's label those angles. Let's label this angle here angle capital B, and let's label this angle capital A, or angle capital A. Well, across from angle capital A, that's little a, side length little a. Across from angle capital B, that's side length little b. And now I can plug into my equation and end up solving. So the sine of angle B, use my math notes here, the sine of angle B we said is 120 over B, which we said was x. And then I have the sine of my capital A, which we said was 28. And across from that was my little a, which we said was 10. Now from here, I can cross multiply and solve. So x times the sine of 28 gives me x times the sine of 28. Set that equal to the other cross multiplication, which is 10 times the sine of 120. Divide both sides by the sine of 28 to get x by itself. And I get, I'm going to take one more space there, x equals 10 times the sine of 120 divided by the sine of 28. And there, if you calculate this in your calculator, you have an answer for x. So again, what's happening here in the law of sines is you have your angle, sine of your angle, you can choose which one's A and B, sine of your angle divided by the side across from it, set equal to the sine of your other angle divided by the side across from it. Okay? And we can do that on any triangle. It doesn't matter if it's a right triangle or a non-right triangle. You can always use your law of sines, which is crucial for us because if we're given this situation, and the situation is this, two angles, side lengths across from both angles. One you're going to know, one is going to be a variable. So two angles that you will know, and then a side length you know that's across from one of your angles, and then the other side is going to be a variable, something that we're looking for. You see a situation like this, you can use law of sines and you set it up again as the angle, sine of the angle, divided by the side across from it. Then it's equal to the sine of the other angle divided by the side across from it. And it works for any triangle. Okay? Here's just a way that they write different ways to say it because some people like to see it as B and C and A and C, and the way that that could look would maybe look as a generic triangle, something like this. This would be your angle A. Across from angle A would be your small a. This could be your angle B. Across from your B would be your little b. And then this could be your angle C. Across from your C would be your little c. And then you could use law of sines for this one as well. Any questions throughout this? Any more problems you want to see that are law of sines, just reach out and ask. I got plenty of law of sines problems to give you.